Some of you may have joined the AMP webinar that Becky Gibbs Murray, our Senior Product Manager for Compliance Software, and Andrew Holle, our Principal Systems Architect, did. I think that was last month. They're going to do sort of a shortened version of that right now. There's also, if you're interested in what they're talking about and you want to learn more, of course, we'll provide their contact information, but you can also view the whole webinar. And there's actually an associated paper that we're going to update and make available as well. Andrew probably just learned that. So Andrew, thanks for signing up for that, for finishing that up. Becky volunteered you. So without any further ado, thank you to the two presenters. Thank you to our customers and for joining. And I'm going to let the smart people go.
Okay, thank you. So if you're considering applying machine learning to your pipeline safety program today, what would that take? How hard would that be? Is it going to be a major expensive undertaking? I need a room full of PhDs to do investigation and invention, or can I just ask Siri? Is the technology mature enough that I could use ChatGPT? So to answer that, we did the following. We took the PHMSA public incident data along with the annual reports. We ran that through an off-the-shelf Bayesian network machine learning tool. And we did that with a couple of engineers, Becky and myself, who are eager and clever, but neither of us has a PhD in data science, and to see how far we could go. So doing that, getting the data, the first thing I'm going to do before I put on my machine learning hat, I'm going to have my engineering hat on. I'm just going to get my arms around the data and see what kind of totals am I looking at. And so here's a summary. And I think these numbers are probably familiar to everyone on this call, but in particular, I wanted to call out, the lower rows. So this is the number of incidents that involved an injury or a fatality, and then the total number of injuries and total number of fatalities. And again, this is out of the data set that we chose, which is 2010 to present. And at the time we did this, it was really around third or fourth quarter of 22. And then you see the average and max cost of an incident, on a pipeline. And so this is the data we're looking at, gross totals. Here's what we're dealing with. And so focusing in particular on liquid, we see the following. Can you go to the next? Thank you. Yeah, just some trends. You see gas incidents have been flat for this whole time, but liquid incidents are trending down. That's good. So the totals are trending down. And so then after this, I might look for an interesting histogram. And so on the next slide, you see, I have a theory that the age of the pipe might matter a lot in terms of incidents. And I see that, in fact, they do. And there's a very interesting curve here. So if you just click once, if you're familiar with the semiconductor or consumer electronics industry, you know about this bathtub curve phenomena, where at the beginning, when a product, or a piece of equipment is made and installed, you get a flurry of incidents at the beginning because there may be a manufacturing issue or an installation issue. But then things flatten out and you run for a period of time in a stable manner, and then the thing starts to wear out. And so your incident rate starts to go up again. And we see that here. However, we noticed, and you see here, that the miles of pipe installed in a given decade is anything but uniform. There's way more pipe installed in the 60s and 70s than in the 90s and 2000s. So our data is skewed, and so to normalize that, we see, no, it's fine. And so we normalize that, and we see that, in fact, the curve looks more like this. This is a more accurate representation. We still have a bathtub curve. Instead of a 40 to 50 year span, it's got maybe a 70-year span. That's better. So again, interesting insight. But at this point, I'm with my engineering hat, I'm kind of stuck. I'm out of things that I can readily do with Excel, but I've got a set of questions, important questions that are unanswered, and they have more to do with probabilities. And these are things that I really want to know about. And so now I need to go further. And so, Becky?
So taking a step back real quick, talking about some of the incident data that we're looking at. We were thinking about pipeline incidents, severe pipeline incidents, as what we're calling Black Swan events. And so rare, but really significant. And so some of the recent examples, some of the big drivers in the mega rule in general, with San Bruno being kind of the industry Black Swan of the previous decades in 2010. But in general, these are some of the incidents in the data set that we're looking at. And so the process that we undertook here, we started just looking at the incidents themselves. We pulled all of the incident data from PHMSA from 2010 to present, and started to model that. But what we found was we couldn't really get a holistic view into what some of the numbers were telling us, because if you just look at the incidents themselves, you start to see, oh, well, Texas is a problem child. 40% of the incidents are in Texas alone. But then if you take a step back and you think about the miles of pipeline in the ground, Texas, Oklahoma, and Louisiana have a lot more pipeline miles than the rest of the country. And so we found ourselves in a situation where we were in a data desert. We couldn't get further in the analysis. And so what we ended up doing was we pulled both the incident data and the PHMSA annual report data that gave us the common denominator we were looking for in order to be able to normalize our data set across all of the different pipeline miles. And we fed that into a tool called NIME. It's a free downloadable tool that lets you manipulate large sets of data in a way that tools like Excel and things like that can't do. And then once we got through that process, we pulled it into a Bayesian network tool, starting from 650 variables. NIME got us down to 68 variables that we used to train the machine learning model, both in supervised and unsupervised learning over various target nodes. And then from there, we were able to determine that there were about 24 variables that truly mattered to the data set, and then a bunch of noise in there. I mean, if you think about the kind of information in those annual reports and incidents, there's a tremendous amount of data in there that like, you know, addresses and stuff like that don't play into the actual analysis. And so that was where we started from. And then from there, we were able to find some pretty interesting results. And so just looking at cost as you know, the target node that we were looking at, there were some notable top contributors. So there were things that we expected to top the list in terms of contribution to incident cost. Things like how much was released, where it was and what happened, and whether or not water got contaminated. All of that we expected to come into contribution as top contributors to cost. What we didn't expect necessarily were that 2 of the top 3 contributing factors were who was operating the pipeline and the manufacturer of the pipe. On the other side of the fence, things that we expected to be low contributors to the cost were the likelihood of failure to the pipe. You know, whether or not a pipe is going to fail doesn't necessarily mean it's going to be an expensive or least expensive incident. Whether or not there was a SCADA system in use, and whether or not there was employee drug testing, we didn't necessarily think that was a player in terms of cost driving. On the other side of the fence, things that we didn't necessarily see being low contributors were whether or not there was an explosion, injuries, or fatalities. We thought those would be a lot higher on the list than they ended up being. Whether or not there was an area that got evacuated, whether or not it was an HCA, and whether or not the pipeline had a service interruption. We would expect that if a portion of pipe goes out of commission for a bit of time, that it would drive to a higher cost than where it ended up falling in the contribution. And then from there, we took just a scenario. We took a pipeline operator, and then we said it's a crude oil going in a pretty standard type of pipe in Oklahoma that was laid in 1990, acquired from US Steel. And we put all of that into the model, and we just said, okay, where's my cost profile for this scenario? What am I looking at in terms of like potential average cost of a pipeline incident for this scenario? And we found that it's around $130,000 as a mean average cost for that, with a really broad breakdown of likelihood of failure, as you see on the bottom. It's kind of all over the board. And then from there, we kind of expanded on the model and said, what are my likely causes and outcomes? I realize this is a very busy slide, so we're just going to break it down a little bit here. On the left, we see on the top left in the box, you see the cause, and we're looking at a 60% chance here that with this scenario, with this operator, in a crude oil pipeline, Oklahoma, 1990, acquired from US Steel. So this specific scenario, it's a 60% chance that it's going to be equipment failure. Going down on the left-hand side, it's going to be either most likely the pipe, the pump, or a valve. But then if you look on the top right over here, then we're starting to see that it's 63% chance it's going to be an above ground incident. So you're not going to have to do digging to fix the problem. It's more than likely going to be on an operator controlled property and not on the main pipeline right of way. Looking at some of the other information here, release barrels, the average there, it looks pretty broad in terms of probability there, but 127 barrels was the average, with a service interruption average of 60 hours. Really high chance that nobody's going to die or get injured. We will most likely contaminate soil, but no wildlife or water contamination and no emissions. If we expand on that though, and say, okay, so what does this exact same scenario look at? So not changing any of the incidents. We're still talking about that Oklahoma pipeline that was laid in 1990. And we set the cost to $1 million. So what has to happen for me to get that $1 million incident? That's when things start to get scrutinized a little bit more heavily. And so in this scenario, when you're looking at $1 million incident, where in the previous slide, equipment failure was really the top contributing cause. Now we're looking at corrosion failure too. It's come into play here. And then 38% chance that it's going to be the pipe itself. Looking on the top right again, it's more than likely going to be underground now. So now there's excavation involved. A much higher chance that it's going to be out on the main pipeline right away. And then some other notable differences is the service interruption went from 67 hours to 162 hours, which is just shy of a week. It's like 6.7 days, I think. And then some other differences is water contamination. The chances that the answer to that is yes went up. Still no fatalities or injuries or ignitions. So from there, we kind of started to look at, are there states or regions in the country that have a higher failure rate or a higher failure cost than others? And so just looking at the likelihood of failure for the country as a whole, some of those the same ones from previous slide here, Texas, Oklahoma, and Louisiana have a higher chance of having a failure rate than other areas of the country just because of the miles of pipe in there. However, when you start to focus in on the individual states and what the likelihood of failure per mile of pipe, and so we're using that miles of pipe to kind of normalize this a little bit. Texas and Oklahoma are actually quite low. So your likelihood of failure for any given mile of pipe is significantly lower in Texas and Oklahoma than in Louisiana, which is the highest in terms of states in the country for likelihood of failure for a given mile of pipe. Thinking about the kind of, climate of Louisiana, it's wet, they've got hurricanes. That likely has something to come into play there. Another higher state that came on the list is California. California has a higher chance of failure than both Texas and Oklahoma, which we found pretty interesting. And then looking at cost, so average cost for a pipeline incident in the entire country is $674,000. If you look at individual states, Louisiana again tops the charts at just under $1 million per incident. California came in really high too at $767,000 average for a pipeline incident. And then Texas and Oklahoma are significantly lower than those two states, which was an interesting find as well.
So if we go back to this notion of the bathtub curve, we ran another experiment, and again, I should have pointed out all the variables in the Bayesian network are probability distributions, and so that's what we're looking at. And so, we wanted to see, do failure profiles shift with where you are in that bathtub curve? And so we ran 3 queries. What does it look like? What is my profile at year 1? What is my profile at year 40? And what is my profile at year 80? And so we do see some shifts, and I think these are interesting and insightful. First, significance increases pretty dramatically across those, and that's the PHMSA definition of an event that is considered significant. There's a criteria there about release amount, total cost, if there's an injury that requires hospitalization, if there's a fatality, et cetera. And then cause. So here at the beginning, so at year 1, it's most likely going to be equipment failure. So think, pumps, valves. Here, and the leak type, is going to be a seal or a packing failure that's above ground. A likelihood of 0.4%, that's per mile per year. And then an average cost of, over $600K. At year 40, this shifts. Corrosion now comes into play. It'll be underground. It'll be the pipe. The likelihood is dropped, and by 25%, and the cost of an incident has doubled. Out at year 80, you see the trends continue. Now corrosion is still in play, but now excavation has come on the scene. And this is third-party excavation. Think of somebody operating a backhoe and not knowing that your pipe is there and hitting it. Again, underground, it'll be the pipe. Likelihood is dropped to 0.1%. That's 4 times less than at year 1. We found that very interesting. Still a higher cost. And so with that, next slide.
Maybe.
Yep.
Trying.
Here we go. We go back to this Black Swan event. And we put in what's my worst nightmare? What keeps me awake at night, and what would that look like? And so we entered our scenario again. An operator that shall not be named. Given these parameters, and now we're entering evidence on the left side saying we do have a fatality. There are injuries. There's ignition. There's contamination. Public has to be evacuated. And so what does that look like in terms of consequence and outcomes? So the release is much higher, around 1,500 barrels. It's going to be a pipe out on the right of way. My likelihood is about 0.2%. It'll be corrosion. It's going to be a $10 million event. That's what this tells me. And I'm going to be offline for a week and a half. Now, that's valuable to know because that's actionable intelligence. I can look at this and see my worst nightmare is going to involve these factors. What can I do? And even though we know our industry is driven by regulatory compliance and schedules that are specified, there's still some flexibility. So for instance, with surveys and inspections, it's possible to, so I'm still back on the slide before, thanks. Yeah, so it's possible to do things like adjust surveys. Maybe I'm going to choose to do my close interval survey instead of next year. I'm going to choose to do it this year. And I can get a crew walking the center line of my pipe. We know that most leaks are preceded, most major incidents are preceded by small leaks. And so having a crew walk that center line and look for pools or dead vegetation could help me identify that incident and address it before it's a major, this $10 million, my Black Swan kind of thing. I could hire a plane to fly the right of way and take a high def video to look for the same. I could run an inline inspection. I could run a tool through and look for anomalies. Even reviewing shut-in and containment procedures can have a dramatic effect. Years back, I worked for a major oil company, BP, and this was during the time of the Exxon Valdez incident in Alaska. And it turned out that that spill occurred. The tugboats and the floating booms that are supposed to be staged for very rapid deployment weren't ready. And so it took many hours. There were delays to get those deployed. And so the spill wasn't contained. And then you had the contamination that followed. Even valve inspection programs, does my shut-in valve actuate? Can mitigate these events and lower the frequency and the severity of these major events. And so, thank you, Becky. If you can go to the next slide. So then that brings us to, well, what is the value of proactive preventative maintenance? And we found that we can quantify that with this model and show that if I choose to just do the average, that's the middle column, that the rest of the industry does of, about one repair, and these are not incidents, these are repairs that we do as a result of inspections, about 1 per 10 miles, I'm going to have this risk and this probability of significance. If I choose to do no repairs, you see that my risk goes way up, right? It more than doubles. Or if I choose to do the average number of repairs that everybody else does, sort of the best citizens, I can significantly lower risk, and risk is calculated as PHMSA would prescribe. The IM folks would know about this, and the probability of significance goes down as well. And you can see the trend on the right. This gives hard data to the maintenance director who's going and defending budget for the coming year. And so using this can, again, help lower the number of incidents and the severity of those incidents. And so going forward, in conclusion, we found some surprising top drivers. Who runs the pipe? Who makes the pipe? Right up at the top. You can always expect a data desert. That's just, it comes with the territory. The incident profiles shift with time. That's the bathtub curve. And then to answer the original question, where is the state of the art? This is definitely accessible to engineers, to capable engineers. There's still plenty of work. This is not a Siri or a chat GPT question yet. We're nowhere near that. And there's no escaping the need for domain expertise of the data. You still have to know. You can't drag and drop a CSV file into a box on a web page and get a trained model out that you can use and have it be of any value. So where could we go from here? There's several options that we looked at. I wanted to highlight one in particular down at the bottom, if you can advance one, Becky. So The non-public operator data, we stopped short. We just went with public data. But if a particular operator chose to go further with this, could take advantage of the public data because that informs the model, but also to include private data with a lot more fine granularity, could come up with some really precise predictive models that would be valuable for them. And then to finish up here, we have some references for things that we looked at that we'll include in this talk that you're welcome to go look at. And now we'd like to leave time. If you have any questions for us, we'd love to answer them now.
There was one question earlier, Andrew, that Justin answered, asking about the incident data and whether it was about CP failures, which is not just CP failures. So I think we answered that question. Anybody else?
Yeah.
You can also raise, I think, just go ahead and drop a message in the chat here.
Well, I know, excuse me, I know when the team did this, when Andrew and Becky did the full hour session on this, we got a ton of questions. So thank you, Andrew and Becky. I think you guys did a great job of.
Hello, this is Madana. Can you hear me?
Yeah.
Yes,
Oh,
we can hear you
yes.
now.
Yeah. Are you also trying to apply or considering applying a probabilistics into the data, what they call analysis? Like you can indicate applying probabilistics, whether an additional inspection or the type of inspection or the number of inspections or any other hydro tests or other things what contribution they can make towards reduction of failures.
Yes, exactly. And with any investigation like this, you tend to generate far more leads and lines of inquiry than you begin with. And that is one of them. And we actually listed that. I know we blew through it pretty quickly. It's on the slide a couple back. Exactly that, to go more deeply into the type and number of inspections that were undertaken. And those are part of the annual reports. So that is absolutely a direction that we can go.
Okay, because in fracture mechanics, that is an advanced methodology to indicate what the advantages and disadvantages would be in terms of the options available to handle any particular issue. So
it would be, yeah, absolutely. Yeah. And that would fall in the category, I think, of sort of private data for a particular operator as well, because those details are usually not included in the incident reports or the annual reports.
Okay.
And we're at the bottom of the hour here, and there are a couple questions in here. I'd say let's continue on, but we realize some people have to drop off, and we'll also be posting this recording on our website and sending you all a link. Question one, who in the industry is leading the predictive analytics? Who do you think are the leaders in our industry, I would imagine?
I think we would
that,
say we don't. What's
ahead,
that? I would say I don't know. We're on a learning curve, and we're trying to prioritize areas where it would provide the most value. But at this point, we're not looking at anyone else and going, "Wow, they're doing a great job. Let's try and do that." I mean, Andrew and Becky, correct me if I'm wrong, but I think we're sort of forging our own path here a little bit.
We are. We know that interest is there. We don't see a clear leader yet. Obviously, we'd like to be that leader. I don't know, Becky, you were at the national conference.
Yeah, I'd say exactly what you said, you know. Just kind of us dipping our toe in the pool, if you will, in terms of what we're capable of when it comes to machine learning. And so AI's got a lot of work in store in terms of how we can add value to our product offering by leveraging some of the capabilities that are available today.
And then I think the second question is actually, if you look at this presentation, it provides a link to the PHMSA data correct, Andrew?
That's correct. Yeah, it's in the top of the references.
Yeah, that's where you can find corrosion leak per mile per year data, right?
Yeah,
Yep.
I mean, it's definitely buried, right? Like there's a lot of information in there, and so you have to go through a process of combining various different data sets and joining different columns together in order to get to a place where you can get it broken down very cleanly. That's what we used that 9 analytics platform for, is kind of that data analysis layer before we used the Bayesian network tool.
Okay, I think it's a wrap, unless somebody has one final question.
As I said, how the machine learning model or AI connect with the operating data. I guess that'll be the last question.
Yeah, so we stopped short of that. And operating data, I'm assuming, temperatures, pressures, flow rates, that kind of thing. That's where we stopped short. That kind of detail is really not included. Well, that's a data desert in terms of public data, but that would also be a great candidate for private data if a particular operator wanted to build out their model with their operating data to try to give predictions around that prime candidate.
All right. Well, thank you, everybody. Thank you, Becky and Andrew. We appreciate it. As I mentioned at the beginning, the full hour-long version of this with a pretty in-depth Q&A is available. And this, of course, is available. And then, again, there'll be a white paper. So thank you, presenters. Thank you for everybody for joining us. Thanks to the AI marketing team for putting this on. We appreciate it. We'll see you next month.
See y'all there. Okay.
Bye-bye.